Hi, I'm Ian Buck. I'm the general manager for accelerated computing at Nvidia. I run the general business, but my background actually is in software and engineering. I started out as a researcher at Stanford, actually, looking at the beginnings of GPUs and how they could be used for more general purpose computing. And I joined Nvidia and started the CUDA project many years ago. And I'm here today to talk to you about the progress we've made, the science, and some of the new stuff that we have in our booth here today. So, next slide. Clearly what we're most proud of is the science that GPUs have enabled here at supercomputing. These are some of the apps that are being pushed in the DOE community around really changing the way we do science and do simulation. S3D, a model combustion for high efficiency engines, really being able to simulate engines and motors and combustion down at the molecular level to build a more efficient car. LAMPS, which is a biofuels, research in next generation fuel technology, green energy, there's a ton of interest that's happening in weather simulation. All of these codes in de novo in next generation sort of fusion reactors. All of this science is really becoming possible because GPUs are adding a whole new level of performance to simulation, where they can actually simulate on the scales that are really necessary to move the ball forward in HPC and simulation. Some of the other successes that we've been having, particularly is in the molecular dynamics. With MD codes, this is research where basically you're trying to understand disease, you're trying to understand proteins, you're trying to understand how things happen in our bodies. Professor Vijay Pandey at Stanford has a project called Folding at Home. And his whole mission is actually it's actually a screensaver that you download onto your computer, and he uses their spare cycles of your PC to simulate protein folding. And this is kind of important because the shape of a protein as it folds in water is critical to its function. Not just the chemicals that make up the protein, but its actual shape. And if it folds one way or a different way, you get a different result. Dr. Pandey, a few years back, actually added GPU acceleration to this code. He just added a GPU to move his molecular simulation, which is basically simulating all these atoms and the forces between them, all onto the GPU. Today, as a result of that, only about 10% of the PCs that run his code actually have a GPU capable of running his software, but it makes up over 90% of his computing capacity on sites all over the world, as you can see here. As a result, he's actually able to do real studies on real science, particularly around Alzheimer's. And he's actually detected a misfold of one of the proteins that happens in the human brain that can actually lead to cell death, the kind of cell death that they think may be the cause of Alzheimer's disease. So this kind of science is fundamental and really is becoming possible because you have millions of atoms in these simulations. You're not just the protein itself, but you've got to simulate the water molecules all floating around. And you have to fold the protein hundreds of thousands of times until you find the distribution of different shapes that it can make. And really it's become possible because he's moved his code to GPUs and delivered that performance. Other successes are actually a new field that's coming up more recently is machine learning. This is the idea of using computers to figure things out that they wouldn't normally think you could figure out, particularly in the area of neural nets. Google built one of their data center projects was a 1,000 CPU server to do a neural net simulation. A neural net is just simply a mathematical simulation or simplification of what happens in the human brain. They built a 1.7 billion parameter neural network. Think of it as 1.7 billion neurons. And their use case was actually YouTube. Google has a problem. All these people are uploading videos to YouTube, and the computer has no idea what's actually in these YouTubes. And if they could figure out what's in the YouTubes, they would search better, they could do better advertising, they'd actually maybe figure something out about them so they'd generate better results for their YouTube customers. This research didn't go unnoticed by the academic community, and they've actually now proven that switched over to using GPUs. This is research by Andrew Ng at Stanford. He's built a 11.2 billion parameter neural network, 10x, and he's only using 16 GPU accelerated servers to do it. With this, he can really process massive amounts of data. One of the newest applications for GPUs today is applying neural nets to all sorts of computer vision, image processing, big data analytics problems. And if you think about it, this kind of simulation, this scale of simulation is perfect for GPUs. There are, there are thousands of threads, billions of neurons. It's a massively parallel problem. In addition, we're starting to see adoption of GPUs in sort of Web 2.0 and kind of cloud computing applications. One of the cool success stories we have is Shazam. So Shazam is, I don't know if anyone has ever used it, you hold your phone up to the radio and push a button, and it tells you exactly the song that's playing from a few seconds clip of the radio, and what the song is, and then of course there's a buy now button, and that's their business. Shazam is one of the most popular apps on iPhone and Android. And people, they have a huge amount of users. They get over 300, the latest statistics are 300 million user queries per month, and they have an index of over 27 million records. This growth was, the more records they can have and the more users is great for them, but it's also a scalability problem. They were using CPUs before, but it was getting harder and harder to search that many records with that many users. They've now switched to GPUs entirely, and they have hundreds of GPUs in their data centers, and this is able them not only to keep up with demand on songs, but they're breaking out into TV. You might see some of the Shazam ads on the logos. They want to do movies and all sorts of other stuff. So this is another case where big data analytics, those kinds of problems, really make a difference with moving them to GPUs. This is the last one. A fun example I'll also give is fire simulation. This is actually a screenshot from one of the Harry Potters, I believe. There's a company called Double Negative, and they had a problem. They want to do really realistic fire simulation for their movies and water and all sorts of stuff. But unlike HPC, where you set up a bunch of initial conditions and let the fire go, you kind of come in the next day and all of a sudden the fire happens to be looping back and hitting the dragon in the face or burning this gnome over here who wasn't supposed to die. And the director says, don't do that. But, how do you do that? You only have the initial conditions of what came out of that dragon's mouth. So they actually built a domain-specific language called JET, and you program in this language, and you can describe how the fire wants to work. The language compiles down, and you can run it actually on the GPU. Instead of taking 24 or 48 hours to simulate, it takes only about a few hours. And so this allows the director to sit right with the technical lead and give feedback on how the fire is looking, and then reprogram it and rerun and fix it for them in kind of real time. They're using this so if you see the new Harry Potter movies and all that kind of stuff, that all that water, all that fire, it was actually rendered all by GPUs and simulated with GPUs today. So, we're here at Supercomputing. Certainly there's a ton of science here. I don't need to tell you about it. You can just walk around and see it on GPUs. But I also wanted to share with you some of the fun things that are happening outside of traditional HPC that's really around big data analytics, simulation, imaging, computer vision. It's fascinating. So I'll also give an update of, where are we with CUDA? Certainly we've been driving CUDA for over 6 years now. We have over 14,000 institutions that have registered CUDA developers with us. We've just crossed the 2 million download mark for the CUDA Toolkit. That's pretty good, given the fact that the CUDA download right now is running about 1 gigabyte. So there's all sorts of good stuff in there. And then we made a very important decision in the very beginning of CUDA and GPU computing. Is we just made sure it was available on every possible GPU, down to our low-end GeForce GPUs and all the way up to the high-end Tesla solutions. As a result, to date, we have over 487 million CUDA-capable GPUs out there. If you have a laptop that has Nvidia in it, you can be programming the same programming model, the same tools, the same language that's being used on the Titan supercomputer in Oak Ridge, or in China, or in Europe. And that really has helped grow this ecosystem to the point where over 700 university courses have CUDA in their curriculum in over 62 countries. So that access has been really, really great. Part of it, though, is also to enable the rest of the developer ecosystem. We've been pushing forward CUDA as a sort of a development platform for people to get access, but our general goal is to enable all developers. And just like you have a programming language, you have lots of different programming languages for CPUs. There's C, C++, Fortran, JavaScript, HTML, Perl, Python. They all exist for really good reasons. we feel the same way about GPUs. There's not one way to program GPU. Depending on who you are, are you a scientist, a web developer, a scripter, a mechanical engineer, there may be different ways to want to program GPUs. So our goal is to sort of help and enable and open up and provide access to GPUs in all different kinds of programming environments and solutions. And that goal of ours is to sort of embrace standards and drive to key languages. One of the most successful ones, one of the most excited about is C++. The C++ Standard Committee has stated for their next version of C++ is they're going to add support for accelerated computing, get access to GPUs, add parallelism to a mainstream language like C++. It's really tremendous for us. And then all sorts of other interesting stuff happening with Java, which I'll talk about in a minute. R, JavaScript, even Python. Last year we talked about that. GPU acceleration has been added to Python at this point. To help do this, we worked on helping the compiler community, because obviously, we got to enable all these people to be able to compile to GPUs. Last year we talked about llvm. llvm is a really cool compiler that's sort of taking the sort of PC industry by storm. It's the default compiler for Apple. It's used by Android. It's used by iOS. It is a wonderful platform. We use it internally to compile for GPUs in our CUDA compiler. We've open sourced our changes to llvm and pushed it upstream to the llvm standard, so now llvm can compile for GPUs. By doing this, we can enable all sorts of new languages on top of GPUs and help that vision, those other languages move forward. But more recently, actually, this just got announced last week, and this is actually an announcement by the OpenACC and Oak Ridge, is that support for GPUs and compiling to GPUs is being added into GCC. So GCC, this is work being done by Mentor Graphics and Samsung. They're actually adding into the mainstream GCC branch support for compiling to PTX, which is our assembly layer, compiling for GPUs. This will be part of the GCC main baseline. If you get GCC with your Linux distribution, Red Hat, Ubuntu, whatever, you'll pick this up. As part of this, they'll be adding OpenACC support, which is our directive-based solutions for GPU computing, but certainly enables other languages to be built on top of this GCC framework. So this is a very exciting movement for us. It's actually being funded partly by Oak Ridge and the OpenACC standard body. It wouldn't be supercomputing without a new accelerator. We have a new accelerator to talk about today, which is the Tesla K40. It's the world's fastest accelerator. It's faster. We took it up to 1.4 teraflops of double precision performance. It has over 2,800 CUDA cores in it and 288 gigabytes per second of memory bandwidth. So you can see what that means for applications taking from our previous fastest to K40. You're getting a nice speed up on benchmarks like Amber. It lets them cross the 4 nanoseconds a day simulation time. In addition, one of the other great features about K40 is that it's double the memory. Previous GPUs, we had a 6 gigabyte GPU was the largest configuration. We've bumped that up to 12 now. And one of the reasons is for some simulations like fluid dynamics and seismic and rendering, they really need big models. If you're simulating a car and trying to do ray tracing on a car, you want to fit the whole car in there because a ray could happen to hit some part of the car, bounce, and hit some other part of the car. You want the whole car model in. So being able to have 12 gigabytes really lets you fit the entire model in. The last feature is called GPU Boost, and this really makes GPU computing, so our GPU is a little smarter. The way we do this is we're able to unlock the extra performance by using untapped power budget. And I'll explain what that is. Basically, if you run a variety of different applications on a GPU, they actually will consume slightly different amounts of power based upon how they're using the GPU. If they don't use double precision, they use double precision, or they use a lot of memory bandwidth or more compute. You'll actually use, instead of the 200 watts, you may only use 180. What GPU Boost does, it allows you to tune your GPU to the power consumption of whatever your app is. So you can go in and run Amber, check on the power consumption, and actually clock up your GPU to a faster performance, use a little bit more power, still within the budget of the GPU, and get that extra boost of performance. This is totally in developers' control. One of the important things about this is you're going to be running this in a computing setting with a server. You want all the units to work at the same performance, so they all work together. You don't have crashes or collisions in MPI. So this is all usable, controllable, and provides some really nice speedups. We call that GPU boost. In addition, last week we announced CUDA 6. This is our latest version of CUDA. And the primary feature of CUDA 6 is called unified memory. To explain what that is, before unified memory, this is how developers program GPUs. You often had a view of two kinds of memory in the system. The CPU memory, the memory that you attached to the CPU and was able to compute it on the CPU, and GPU memory that was fast and computed on by the GPU. The developers had to think about these two memory spaces separately, allocate memory here, and move the data back and forth explicitly to wherever you're going to operate on it. With unified memory, we've moved this memory management and data movement into the runtime and into the drivers. So now the developer sees a single view of memory, and the data just moves seamlessly from whichever processor wants to operate on it, without having the developer do that manually. What that means for developers is it greatly simplifies programming. This is a simple CPU program that's doing a simple sort. And on the GPU with CUDA 6, you notice you change the allocator function, a very simple allocator function up here. At that point, memory management is done by our drivers, our runtime. You don't have to worry about it. And as you access it on the CPU or the GPU, the data moves seamlessly to and from, all being handled by our drivers under the covers. Developers, of course, can still optimize for the memory hierarchy. But this makes it easy to get your codes up and running on the GPU with some nice speedups, and then you can optimize further if you want to. So this is one of the major features of CUDA 6, unified memory. In addition, we've been working on our library stack. We have a new drop-in NVBlast Library. The idea here, if you're using BLAS, the standard BLAS library from NetLib, this is a drop-in replacement. So we've now, using the unified memory technology, we can actually you can replace your existing BLAS library, put in our BLAS library, no code changes. You can either recompile with it or change it with NV preload, and the BLAS library will just pick up our BLAS, and now all your matrix or BLAS 3 functions will happen on the GPU seamlessly for you. So we'll move the operations, their data over there, execute on it. You get the benefit of the GPU without actually having to program it if you're using BLAS. This is another nice programmability feature. In addition to this, we've been working on multi-GPU. More and more, we're seeing people put not just one GPU with one CPU, but one CPU with 2 GPUs or 4 GPUs. I've even seen configurations going up to 8 GPUs. With our library, we actually have now auto-parallelized our BLAS library to scale across multiple GPUs. So in the drop-in case, or if you're programming with our existing BLAS libraries, BLAS will now scale seamlessly across multiple GPUs for all BLAS level 3 routines. So just drop in another GPU, your code goes, you can see it, roughly 2x faster. Nice speedups. And it can't get any easier than just popping in another GPU. Okay. That's CUDA 6. I think we have a couple of other fun announcements that you definitely should check out here on the show floor. First is the Peace Date system, which got announced this morning. This is a new supercomputer hosted at the CSCS Supercomputing Center. It's 6.27 petaflops. It's the fastest supercomputer in Europe, achieving over 80% limp pack efficiency. It's also the greenest petaflop scale supercomputer in the world. It's over 3,000 megaflops per watt on the Green 500. That beats the previous number one by a mile. As you can see, almost 50% more efficient of a supercomputer. What I like about this system is that it actually is targeted at solving a really good real problem, which is weather simulation. And weather simulation in Switzerland, as you can imagine, is kind of hard. The geography there is not easy. And their goal is actually to simulate weather down to the 1 kilometer resolution for all of Switzerland. If they can accurately predict weather in a country like Switzerland with the geography that it has and all the mountains and all those villages, it's pretty much a shoe-in they can simulate weather anywhere. So this system is funded is about solving weather. We're thrilled that it's on the floor here, and definitely check it out. In addition, actually, there's, like I announced this morning, was the greenest supercomputer in the world. This is the Tech KFC system. KFC is very big in Japan. It has actually achieved over 4,000 megaflops per watt of computational efficiency. These are servers that are sitting in oil. Actually, have no moving part in the cooling solution. The oil takes care of the cooling for you, so you save all that power that you would have spent on pushing air and fans. That bumps up the efficiency quite a bit. It's 25% higher than the #1 Green 500 system today, and it actually is 160 Tesla K20 GPUs. So a really cool system. They're really pushing the limits of efficiency, because as we know, as we move forward and forward in supercomputing and we get all the way to exascale, really managing power and perf per watt are paramount. We don't have more power to throw at these systems. We have to build more and more efficient architectures, take good advantage of accelerators, and be creative about new cooling solutions and system design to really keep our systems running efficiently. Okay. The oil, I think the company is here at the show floor. What the oil made of, I don't know. You can come back later and I'll talk to you about it. Our last announcement is one I'm most excited about, and that's our new partnership that we've made with IBM. The success that HPC has been able to achieve with Accelerator has not gone unnoticed. As I've mentioned before, there's been some great inroads in data analytics, in enterprise computing, not just HPC. And this work hasn't gone unnoticed. And we announced this morning a new partnership with IBM to work on the new era of computing and big data analytics. Let me give some background. First, a while back, IBM announced a new Open Power Consortium. This was an initiative by IBM which we welcomed and joined from the get-go, which is really to open up the power platform as an open ecosystem for all power and power architectures. People like Linux, and we joined right off the front to make sure that GPUs could be an awesome part of that new power initiative to bring power to broader than just the AIX or supercomputing world. But a bigger part of this announcement is that IBM is working with us to actually accelerate their analytics software. This is in areas of predictive analytics, business analytics, languages, and compilers. In addition, IBM has also talked about how they're interested in accelerating the IBM Java to make it run on Nvidia GPUs, which is a great testament to bringing more of their software solutions and their big data problems to the GPU. In addition to the work being done in the enterprise space, there's also a success that's planned for the supercomputing world. And this is building upon the partnership that we're doing with IBM and the Open Power Consortium to build the next generation supercomputers with IBM. This combines the Power CPU, which is probably the world's fastest multi-core serial processor in the world, an incredibly amazing serial processor, married with the fastest accelerator out there today, the Tesla GPU. So really the combination of the Power CPU and the Tesla GPU enables that next generation of IBM supercomputers and enterprise servers, which we're totally excited about. We expect to see GPU accelerated power-based systems available next year. And to help explain why this partnership is so important to IBM, I'd like to invite on stage Dave Turek. Dave Turek is the VP of Advanced Computing at IBM. I think he is a industry leader and been around the block for a very long time. Critical in the original DOE ASCII and ASC work. Also the VP for all of the Blue Gene work that IBM has done. I'd like to invite Dave on stage. Is Dave here? Come on up. Thanks, Dave.
Thanks, Ian. Get off my stage. So I'm not going to show any charts because otherwise I would have to prepare charts, and I'd rather focus on preparing the comments instead. So when we think about the implications of this partnership, I want to begin by drawing some distinctions between the way IBM views high-performance computing and the way others might view high-performance computing. For many, high-performance computing is defined by an algorithm that needs to be optimized. We define high-performance computing as a workflow that has many elements attached to it, which may have an algorithm to be optimized within it. At the end of the day, what customers want is to accelerate the time to solution, not to accelerate the particular piece of a workflow that may only contribute to 2 or 3% of the overall workflow time. So for us, there's a blurring of the distinctions that people have talked about in terms of big data, analytics, and HPC. We don't believe those distinctions are meritorious. We think that from a workflow perspective, these things are fundamentally interlinked. When you begin to look at that concept of looking at classic HPC coupled with analytics and big data, and you look at it in the context of the tremendous growth of data types, the velocity of data, and so on, you begin to entertain some fundamental notions that you have to deal with. One of which is it's becoming progressively more difficult to move data in the context of your data center, in the context of your solution infrastructure. When you start talking about moving petabytes of data over networks from a storage device to a computing device, it starts to become problematic with respect to latency. So we fundamentally believe that the future is wrapped around the idea that we'll move computing physically to where the data is, meaning that we're going to put computing in devices where data is stored. Our partnership with Nvidia is predicated on the idea that the notion of the computing that we allocate in storage and networks and memory and other parts of the computing infrastructure itself needs to be customized to the nature of the problem at hand. And we'll dedicate a variety of different kinds of technology in this area, but we think Nvidia will play a critical role in terms of getting distributed in IBM products other than just servers. Okay? So servers have been a carrier for Nvidia for a long time. And the postulate in front of you is, given the future of what big data implies, that's no longer sufficient. We have to contemplate the incorporation of accelerators in locations other than servers in the computing infrastructure. So as a consequence, the partnership between Nvidia and IBM becomes strategic. Strategic in terms of giving the absolutely precise kind of computational attributes at the point where data is located, but also strategic in the sense that it gives customers a dramatic improvement in the choice of how they attack the problems at hand. So choice, computational precision with respect to the type of architecture we bring to bear to the problem at hand become critical elements to giving enhanced value to our customers. We'll see this in products beyond what you've seen today from IBM. Today we distribute GPUs in several of our products. The future is going to be substantially more than that, both in terms of product type and the nature of the way in which the GPU technology is presented. I'm not going to announce products today for sure, but you can think back to the architectures we've deployed in the recent past and how we've employed different kinds of architectures to solve complex problems, and your imagination will start to conjure up images that I think are probably not far from where we'll be at the end of the day. IBM's perspective is this is going to be a long-standing, important relationship at a technology level, at a development level, and at a sales level that will sustain for a considerable amount of time from where we are today. It is synchronous with our view of where HPC is evolving. It is completely synergistic to what we think presents value to our customers on a worldwide basis. So on behalf of IBM, we're quite grateful that this has been consummated and we can get down to doing work now. So that's it.
Thanks, Dave.
Thanks, Ian.
I've had the pleasure of working with your team for a while now, and I'm pleased we finally can talk about the work we're doing. And I have to say you have a world-class computing and HPC team, so I'm very excited.
Thank you.
Moving forward. With that, that's my last slide. I think in general, I want you to enjoy the booth. We have a ton of great demos. The K40, we have a MapD Twitter demo here, as well as a RGT car simulation demo. And as well, you can sign up for our developer area, where you can get free training around CUDA and OpenACC. Sign up and take a quick course.
And we also have time for some questions.
Oh, sure. Any questions from the audience? Hi.
Oh, hello. It's really great, great setup. I'm enjoying it.
Great.
And my school have a supercomputing team with 40 K20s.
Excellent.
And I was wondering if you've mentioned K40 boost.
Yes.
Yeah. So would it be exceeding the power of 225?
The power limit of the K40 is 235 watts. So you can dial up to prescribed clocks. As long as you don't exceed that, if you try to exceed that, the GPU will automatically throttle down. So you experiment with it. I think you should be able to play and see how high you can
So it's flexible.
It's flexible, yes.
Okay, I see. Thank you.
Great. Other
Any
questions?
So I understand that you can't talk too much about upcoming products, but when you say moving GPUs away from just servers, are you talking about servers that are just handing out data to clients, or do you mean servers as in away from the server platform and onto appliances or other devices?
Think of it more as appliances. I think the notion of what a server is going to change quite dramatically in the next several years, and I think the ability to crisply distinguish a device as a server is going to go away.
And we are live streaming, so we actually have a couple of questions, and I'll get to one of the questions online. Hold on. Okay, this question is for you, Ian. How can I get access to CUDA 6?
CUDA 6 should be will be available shortly. We're about to open up our release candidate program, which is available to any registered developer. So if you go to developer.nvidia.com and click on CUDA, you can sign up and get notified as soon as it's ready, which should be pretty soon.
Fantastic.
Excellent.
I think that's it for tonight, but like Ian said, there's plenty of time to sit by our booths, go by our developer zone, check out the demos on the K40s, talk to Ian directly, and we'll see you all back here tomorrow morning. Oh, I'm sorry, one other thing. Some people weren't able to get their scarves, and I've been told that if you go by the info booth, they'll be able to scan your badge and give you your scarves. And once again, thank you for coming, and I'll see you tomorrow.
Thanks.
Thank you.